about making discoveries, right? And those discoveries, the major ones, are rewarded with the Nobel Prize, which is the greatest award that any scientist can ever get. First, a little bit of history of the prize itself. Obviously, comes from Alfred Nobel. Specifically, it comes from Alfred Nobel's fortune, which was immense. But let's get into the details. Our story actually starts in Switzerland with Christian Friedrich Schoenbein, a Swiss chemist, who, at least according to the legend, used to sometimes take his work home. And one day he was working with some nitric acid and sulfuric acid, which he happened to spill on the floor in the kitchen. Luckily for him, Frau Schoenbein wasn't home at the time, because she would not appreciate the acidic mess on the floor. So, what did he do? He grabbed the first thing that he could, which happened to be his wife's cotton apron, which was hanging on the nail. Took the apron, he wiped up the mess, but then he had a wet apron on his hands. Had to do something about that. He hung it up in front of the fireplace to dry. And the next thing he saw was that the apron burst into flame and disappeared, surprisingly, without producing any smoke. Schoenbein had discovered a substance that came to be called gun cotton. The apron was made of cotton. The nitric and sulfuric acid reacted with it, and basically nitro groups were tacked onto that cellulose. So what? It made it highly combustible. This came to the attention of Assanio Sobrero, an Italian chemist, who was working with this flammable material. But he wanted to improve upon it. And he wondered if you could react something else other than cotton with nitric and sulfuric acid and make it flammable as well. He tried a variety of substances, but he finally found glycerin. So he reacted glycerin with nitric acid and sulfuric acid and formed nitroglycerin. Nitroglycerin is a high explosive. Some of you may have encountered that in the wonderful movie, The Wages of Fear, when they were transporting drums of nitroglycerin on a truck. And of course, it was over some pretty rough terrain. And the question was whether or not they would succeed. You'll have to watch the movie to find out. So in any case, this came to the attention of Alfred Nobel. Nobel was a pretty noted chemist already, but he wanted to somehow harness the energy of nitroglycerin because, something that just explodes on a little bit of impact is not very useful. So he tried all sorts of things. And finally he found that when he mixed the nitroglycerin with a type of clay called kieselguhr, he converted it into a substance, a solid substance, came to be called dynamite. This was a high explosive, wonderful for building tunnels, for mining, construction, changed the world because it would only explode when you wanted it to explode. Nitroglycerin, of course, would explode on any kind of impact, but when it was mixed with kieselguhr, you had to light it or use a percussion cap. He made a vast fortune from dynamite. But one day, Alfred Nobel opened up the newspaper and saw his own obituary, which said, "Who became rich by finding ways to kill more people faster than ever before, died yesterday." Well, it turned out, of course, that the newspaper had made a mistake, and it was his brother Ludwig who died, but they mixed it up. Well, this, of course, had a terrible impact on Nobel because he recognized that maybe there was something to this, that people were perceiving him as being a murder. Because, of course, dynamite could also be used to the detriment of mankind. He had never intended that. But, substances, of course, are not good or bad. People are good or bad. It all depends on how you use it. And at that moment, he decided that he was going to leave this fortune as a legacy. And here's his first note of that. This is his will, where he said that all his money would be given out in the form of Nobel Prizes. And it was a vast fortune. You can imagine how vast the fortune was, that the Nobel Prize money that is still being given out, and this year it was $3 million, is coming from the interest of his original fortune. The capital has never been touched. So that was a lot of money. And indeed, since 1901, the Nobel Prizes have been awarded. The first Nobel Prize were awarded in 1901 in chemistry, in physics, in medicine, in literature, and in peace. The economics prize was added later. That was not one of the original prizes. But Nobel also wanted the prizes to stimulate further science and further research. So there was a stipulation. The Nobel Prize could only be awarded to people who were alive. It could not be given posthumously. So, although of course there had been a large number of scientists prior to 1901 who had made huge contributions to advancement of science, but they were blocked out from getting the Nobel Prize. The prize is awarded every year by the Nobel Committee, and it is given in Stockholm. It is a huge ceremony, and it is followed by a dinner. Pretty impressive dinner, right? It is in this building in Stockholm. I had the chance to visit there a few years ago. That's the hall where it is all done. So it's sort of, a holy place for any scientist. So anyway, the first set of Nobel Prizes were given out in 1901. And it was indeed a big event. It was widely publicized around the world. So what I would like to do with you here today is to discuss that very first year, the first Nobel Prizes. And they were given in physics, in chemistry, and in medicine. And each of them turns out to be very interesting. One thing about how these prizes are awarded, they are selected by a committee, and that committee sends out letters to solicit nominations from noted scientists. Anytime that you hear that someone says that they have been nominated for a Nobel Prize, that is total nonsense. That is not how it works. But you have people like Trump, no surprise there, who say that they have been nominated several times for the Nobel Prize, He says he was nominated for the Peace Prize several times. He's full of crap, of course. The man is full of crap in every possible way. He's a lunatic. But this is another instance where it's just a lie, because you don't get nominated. The letters are sent out to scientists around the world, and they are asked to send in nomination. And I can guarantee you, no one received a letter and responded that I would like to nominate Trump for a Nobel Prize. That did not happen. All right, so let's start out with the physics prize. And with a historic relic, and there it is. That symbolizes the first physics prize. Anyone know what that is? This changed the history of the world. It is perhaps the most important discovery ever made in medicine, although there are many candidates for that. This is the first X-ray tube that was ever made. And the first winner of the Nobel Prize in Physics was William Röntgen. Now, therein lies an interesting story, and a pretty complicated story. There are stories galore behind every Nobel Prize. One thing to understand, and this holds true for every area of science, is that discoveries do not come just out of the blue. They are based on work that has been done before. Science plods along with steps, and sometimes someone managed to take a larger step, but it is always based on something that has gone on before. And in this case, Nobel was trying to duplicate the work of a Hungarian scientist who was actually born in Bratislava at that time. The Austro-Hungarian Empire encompassed what now would be Slovakia as well. But he had moved to Germany, where he did his research. And his research was on something we call the cathode ray tube. And this was a very, very important moment in history, the discovery of these cathode ray tubes. It was a very simple device. You had a glass tube with a contact at each end, and a battery would be attached or some power supply to the two ends, and there would be a ray, a beam, that flashed across inside of this evacuated tube. These rays were called cathode rays because they went from the cathode, which is the negative electrode, anode, which is the positive electrode. Now, before we go any further, I told you that there are all kinds of stories behind the Nobel Prizes. And there certainly is a story behind this one. Because Philip Bernard, who looks like a nice gentleman, was anything but. He was a Nazi sympathizer of the worst kind. He was a German nationalist. He despised, as you can see, English physics. He considered these being stolen from Germany. He was a proponent of German physics, so that only German science should be considered. He had an ongoing battle with Einstein. He was a terrible anti-Semite, Leonard was. And as you can see, under Hitler, he became chief of Aryan physics. Interesting book, The Man Who Stalked Einstein, that was him. Had all kinds of battles. But his science was good. So, sometimes science and ideology make for very strange bedfellows. So anyway, it was his work on the cathode ray tube that Röntgen was trying to duplicate. But I said, work is always built on work of others. Leonard himself had done his experiments based on the work of Sir William Crookes in England, who was the first person really to introduce cathode ray tubes. And the cathode ray tube is very interesting. As I told you, it's a vacuum tube, so there's no air in it, it's evacuated. And when you pass a current through it, the glass will glow in this eerie glow. Cathode ray tubes can activate glass or any kind of luminescent screen to make it glow. And this basically is the way that the original television sets work and the original computers work. That's how the screen works. The cathode ray tube scans its beam, which turns out to be a beam of electrons. And that's how the phosphor is activated. So Leonard was basing his work on the Crookes tube. And here's what he did. So here's the Crookes tube. As you can see, it's got electrodes at the end and has the power supply attached. But what he was interested to find out was whether or not these rays, this beam that he saw inside of the tube, whether it could also emerge from the tube. So what he did was he made a little window at the end of the tube, covered with a very thin sheet of aluminum. It was enough to hold in the vacuum so air wouldn't go through. And what he found that indeed the ray did go through about 8 centimeters. How did he find this? Because he had a screen that was coated with a luminescent material that would glow when it was exposed to these rays. It was covered with a chemical that at that time was called ketone, and it glowed. But as soon as you moved it more than 8 centimeters away, it did not. So this is the work that Leonard was doing, and this is what Röntgen was trying to duplicate. The only problem was that he couldn't get his hands on any of that luminescent material, the ketone, because Leonard had bought it all up. However, he did find another substance that also glowed when it was exposed to various kinds of light. And this was something that had the foreboding name of barium platinocyanide. It was a yellowish powder, and this is what he was going to try to duplicate the original experiment with. I mean, this was a chemical that had been made by a German chemist. Much of the chemistry in those days was done by Germans, called Leopold Mellin, who was actually very well known. He published a whole series of books on chemistry. I mean, he was so well known that, in fact, there was even a German stamp that was formulated on him. So anyway, so Röntgen was stuck because he didn't have the ketone, but he had the barium platinocyanide. So he set up his apparatus, just like Leonard had, and so he had the screen that he was going to use that was covered with the barium platinocyanide, and he had put it on a bench while he went to connect the electrodes of this vacuum tube. He connected the electrodes, and then he saw something remarkable. This screen, which was meters away from the tube, started to glow. This was remarkable because he knew that this could not be due to the cathode rays, because it had been shown that they don't pass more than 8 centimeters out of the tube. So he had discovered something that was emanating from that tube, invisible. He didn't know what it was. Eventually, of course, he stole the symbol X from mathematics for unknown, and these rays came to be called X-rays. But then came the epic moment when he went to pick up the screen that was glowing, put his hand in front of it, and all of a sudden he saw the bones of his hand, which meant that whatever rays were coming out of this tube were going through his flesh, but were not going through the bones. So therefore you had this image of the hand. He got all excited. He ran to get his wife, Bertha, and he had her put her hand on the screen, exposed it to the cathode ray tube in this fashion, and produced perhaps the most famous picture in the history of medicine, the first ever X-ray. And that's Bertha Röntgen's hand, and as you can see, she was wearing the ring. When she saw this, she was frightened. Supposedly, she said, "I have seen my death," and she never went into his lab again. Within another 5 weeks, Röntgen worked day and night secretly in the lab to make sure that all of this was real and to work out the details, and he did. So very soon after this first X-ray was made, he wrote a letter to the local medical society explaining what he had seen and demonstrating it to the doctors. And it's amazing that this spread like wildfire around the world. In the pre-internet days, and doctors immediately recognized the importance of this, and it was put to use. Of course, it could obviously do X-rays and discover broken bones, etc. It was put into use on the battlefield. Portable X-ray units were set up. It's not that difficult. All you needed was the cathode ray tube and a fluorescent screen. And this was really important on the battlefield because they could visualize where the bullet was. I mean, before this time, whenever someone was shot with a bullet and a doctor had to remove that bullet, they had to poke around and, cut up the body to find the bullet. With the X-ray, you could see exactly where the bullet was. When President McKinley was shot, he was X-rayed, and they found the bullet, and they were able to take it out, but unfortunately an infection had already set in, and he died. He was assassinated. There were mobile X-ray units during the First World War, and of course these needed drivers. And one of the drivers of these X-ray units was this lady. It's not a very good picture, it's the only one that we have, but you recognize who that is? That's Marie Curie. Yeah, she was an ambulance radio truck driver during the First World War. When Thomas Edison heard about this discovery of X-rays, he, of course, jumped on the bandwagon. Edison is recognized as the greatest inventor in the world, which is probably a justified moniker. But his expertise really was seizing some ideas and bringing them to fruition. He did not, contrary to what people think, did not invent the light bulb. What he did do was make the first functional light bulb, commercially available light bulb. Joseph Swan in England had invented the light bulb some 50 years earlier, but was never able to make it work for more than a few seconds because the filaments that he used would burn up. Well, Edison did what Edison always did, trial and error. He tried different materials, hundreds of different materials, before he found something that could make the light bulb last longer. So he was immediately intrigued by the discovery of X-rays, and he wanted to improve on it. He wanted to find a material that was even more sensitive, that would glow better, that would give you quicker X-ray pictures. Because with the first X-ray units, you had to have a pretty long exposure time in order to expose the fluorescent material to enough X-rays. So he tried and he tried. And he eventually came up with a tungsten oxide. And he already, of course, knew a lot about tungsten because that's the material that he had found for filament in his light bulb. And he discovered that this was even better than barium platinocyanide. It would glow very easily on exposure to X-rays. And he invented what came to be called the fluoroscope. And you can see the doctor here with this screen on his head, which had in it the screen coated with this new chemical. Underneath is the equipment to produce the X-rays, the cathode ray tube. So the rays would go through the body, hit the fluoroscope, and the doctor could actually be looking inside of the body. This was actually developed by one of Edison's assistants, who was Clarence Daly. And as you can see, he's demonstrating it here to Thomas Edison. That's Edison looking through the fluoroscope at Daly's hand. Now, the thing is that in these early days, they didn't know anything about the potential damaging effect of X-rays. And unfortunately, Daly eventually lost his fingers and then both his hands from radiation due to the X-rays. However, of course, in spite of that, fluoroscopes, as they were called, were tremendously useful. And here is one instance. Once again, the X-ray equipment is behind the guy. The X-rays go through him and impinge on the fluorescent screen, and the doctor can look. And in the early days, they checked for tuberculosis in this fashion. And I remember that because this was in 1955 in Hungary. I was in grade 3. Everyone in the class was marshaled into the gymnasium in the school where they had set up the equipment that looked exactly like that. And we were all screened with the fluoroscope. Does anyone remember that being done here? No, not mammograph. This was before mammograph. Way before. Yeah. So anyway, I mean, that was quite a common procedure. There was another interesting application of the fluoroscope, and that was in shoe stores. Now that you remember? So in order to try on to see whether or not the shoes were fitted properly, you put the shoes on, you put your feet inside, and then you'd look, and what you'd be looking at were X-rays. And again, nobody at that time knew that, you know, this was really the wrong thing to do, but it was certainly very popular because you got the right size. And X-ray fittings, you found these things in all kinds of stores. Now, of course, the exposure time there was not very long, so not many people got burns. But if you stayed around this instrument long enough, you did get burns. And also, what was interesting that in those days, they used to check whether or not X-ray equipment was working properly by putting their hand in front of the fluorescent screen. That's what they're doing here. Okay, so here's the X-ray tube, and to check whether or not this screen is working properly, you just put his hands in front, and of course you see a shadow of your hand if it was working properly. But of course, you know, they didn't know what radiation was. Well, we've come a long way with fluoroscopes. Today, that's what they look like. Tremendously useful instruments. So the question comes up, what is the difference between X-ray and the fluoroscope? It's a very simple difference. An X-ray is a still picture, right? You get one picture, like the original hand picture. With fluoroscopy, it's a movie. You can actually see what's going on in the body. So the patient lies on the table. The X-ray equipment is below, goes through, there's a detector, and these days it's transmitted to a screen so that the doctors looking at a screen, they're not exposed to the X-rays. So obviously, X-ray was a very, very major discovery. No, but the fluoroscope scan. Okay. The CAT scan is a series of X-ray pictures, still pictures that are taken, okay, by doing different slices through the body. This is, if you see a fluoroscope on, you're looking at a screen. If you're doing fluoroscopy, for example, of the heart, you see the beating heart. I mean, this is what they use when they do an angiogram, right? When they need to put the catheter in, they're looking at a live picture. It's really quite amazing. Now, X-rays had a role to play in chemistry as well, believe it or not. A very, very important role to play. Turns out that if you have crystal of a substance and you expose it to a beam of X-rays, the atoms in that crystal, when the X-ray hits it, will diffract the X-ray. It will spread it around. and you get a series of spots on a fluorescent screen. And from that, you can back calculate how the atoms are positioned within the crystal. And this gives you a structure, this gives you basically molecular structure. And one of the most important such experiments ever done was 1952, Rosalind Franklin, with this X-ray diffraction pattern, which came to be called photo 51 because it was number 51 in a series. And what you're looking at here is the X-ray diffraction pattern that was the clue to the structure of DNA. And Crick and Watson then were able to put it all together and build a model of DNA for which they received the Nobel Prize in 1962. Unfortunately, Rosalind Franklin was not recognized with the Nobel Prize. She should have been. Why not? Probably because she was a woman, and that just wasn't done in those days. But she certainly should have been a part of that, because without her X-ray crystallography, it would not have been possible to solve the structure of DNA. Of course, X-rays also had some, nonsensical connotations. Some of you may remember on the back of comic books ads for X-ray specs and X-ray glasses. I mean, this is just total nonsense, just capitalizing on people having heard of X-rays. And then, of course, there was Superman, or in this case, Superboy, who was, we know, had X-ray vision. Well, of course, he would not have had X-ray vision if the writers didn't know about X-rays. But there was one other interesting connection. Some of you may remember this one. The man with the X-ray eyes. Who remembers Kuda Bux? No. Kudabux. Kuda Bux was a very, very interesting entertainer. And in fact, in 1961, he came to Montreal. As you can see, the man with the X-ray eyes at the El Morocco. Who remembers the El Morocco? On Clossy Street, just opposite the Forum. And that was the place to be. I mean, in the 1940s, 1950s, Montreal was a hotbed of nightclubs. So anyway, you can see Kuda Bux appeared there. Now, what was his shtick? Why the man with the X-ray eyes? Because he supposedly could see, even though he was totally blindfolded. Now, the blindfolding was done very interesting, because he would have volunteers come up from the audience. He would give them some dough, bread dough, soft, buttery dough, put it over his eyes, then wrap his head in gauze, look like a mummy after. Only his nose and his mouth were open. And they would put a book in front of him, and he'd be able to read it. Now, these blindfold tricks are age-old in magic. And it usually is done because no matter how you think that someone is blindfolded, they can peek down the side of their nose. When he was doing this, even with the putty, he'd be kind of helping them put the putty on his face. But he would do it in such a way that there was a small opening. Anyway, that's the theory. He did fool some magicians too. And there's no absolute consensus on how he did what he did, because he drove a car blindfolded, he did bicycle rides blindfolded. He was a very, very good entertainer. The only thing I can tell you is that we need our eyes to see. So somehow he was lucky. All right, so X-rays. Now, of course, the theory, we know all about it. And whenever we have this cathode ray passing between the electrodes, X-rays are generated. And we know that the X-ray is part of what we call the electromagnetic spectrum. And X-rays differ from all of the other types of radiation in the wavelength or the frequency, which are the units that with which we measure electromagnetic radiation. And X-rays are more powerful than visible light and infrared. That's why one has to be very careful with it. The higher the frequency of wave, the more penetrating they are, the more danger they can do. But anyway, today, all of this is understood. And the dosage of X-rays that is now used is very, very small. The equipment is very sophisticated, so that there really is no need to worry. But still, a CAT scan will be much greater exposure than just a single X-ray. So 1901, the first physics prize went to Wilhelm Röntgen, very, very much deserved, of course, because as I said, it really changed history. The chemistry prize. Well, the chemistry prize went to someone who chances are you have not heard of. This is what the actual document looks like when you win the Nobel Prize. This is Röntgen's, and Röntgen was then recognized by stamps around the world. So anyway, the chemistry prize went to Jacob Van 't Hoff. Van 't Hoff, in chemistry circles, of course, is very well known, but not so much in the outside world. He basically explained what osmosis is all about. Now, you probably heard the term osmosis without really understanding what it is, but it's a very basic phenomenon, and I think it's well explained here. When you have something dissolved in a solution, and you have what is called a semi-permeable membrane through which water can pass, but nothing else can pass. Water will go from the more dilute solution into the more concentrated one, trying to dilute it. That's the whole theory of osmosis. And as you can see, on the left side there, the solute, which may be sugar or salt or whatever, surrounded by water. You have different concentrations on the two sides of this membrane. Water will flow in such a way as to try to dilute the more concentrated solution. So here's the end result. Now, of course, as you can see, there's more water on this side than on this side. So there will be a greater pressure on this membrane from this side. This is called the osmotic pressure. Where is this important? Without this, life would not exist, because plants, of course, need water. Well, have you ever wondered how the water gets up to the top of a tree? It all starts at the bottom, and it starts with osmosis. Water from the soil has to pass into the tree. Well, of course, there are all kinds of chemicals naturally occurring inside of the root. The water tries to dilute it, and the pressure mounts and pushes the water of the tree. So that was a very important theoretical explanation. But Van 't Hoff was also important in a totally different fashion. He got the Nobel Prize for this, for the physical chemistry of osmosis. But he also made tremendous contributions in organic chemistry. Organic chemistry is the chemistry of carbon compounds. And carbon compounds are everywhere in the world. Carbon is a very, very abundant element. And Van 't Hoff's contribution was the understanding of the three-dimensional nature of molecules. He, in fact, was the first one ever to make molecular models. And these are some of his original models. He was able to determine that a carbon atom always forms bonds to other atoms in a very specific way. A carbon atom will always form 4 chemical bonds. And these are in a tetrahedral fashion. So here's a carbon atom in the middle, the line. And this is the way that carbon joins to other atoms. Always 4 bonds oriented towards the corners of a tetrahedron. Now this makes for a very interesting arrangement. And this is where the brilliance of Van 't Hoff came in. If you look at these two structures, they both have a central carbon. They are both bonded to a blue, a green, and a red atom. But they are not identical. If you try to place the one on the right over the one on the left, you can make the red line up and the blue line up, but then the white and the green don't line up. In fact, they have the same relationship to each other as your two hands. They are mirror images, but they are non-superimposable mirror images. You cannot put one on top of the other. In chemistry, we call them enantiomers. They're non-superimposable mirror images. What is the consequence of this? The two different enantiomers can behave differently in the body. I'll give you a classic example, naproxen, which is a non-steroidal anti-inflammatory. I'm sure many of you are familiar with that. This can exist in two mirror image forms, but only one of them relieves pain. The other one is toxic to the liver. Well, obviously they have to be separated, and only the active one is in the drug. But one of the most interesting connections here is through fiction. Dorothy Sayers, a classic writer of mystery stories, detective stories, a contemporary of Agatha Christie. Dorothy Sayers wrote a number of great stories, but this one, The Documents of the Case, it's the story of a mushroom collector, an expert mushroom collector, who one day is found by his son slumped over into a stew, a mushroom stew that he had made. Can't figure out what it is, but the coroner takes a sample of the stew, they analyze it, and they find that it contains a compound that is found in the Amanita muscaria mushroom, which is a highly poisonous mushroom. So the theory is that he had made a mistake, that he had been actually trying to collect Amanita rubescens, which is a safe mushroom to eat, made a mistake, and accidentally poisoned himself with muscarine, which is the poison that is found in the Amanita muscaria mushroom. And indeed, it's a highly toxic compound. It's what we call a cholinergic. It increases the amount of a neurotransmitter in the body called acetylcholine, which overstimulates you and basically causes the heart to go into fibrillation, and that's how you die. But the mycologist, that's what mushroom experts are called, the mycologist's son does not believe this, because he knows that his father would never make such a mistake. When you're an expert mushroom collector, you do not pick up Amanita muscaria by accident. I mean, this is something that is very easily recognizable. I mean, it's, you know, there are some mistakes you don't make. I mean, you don't put Drano on your toothbrush, right? So he would never make a mistake like that. But he didn't understand, you know, because the chemical test showed the presence of muscarine. But he knew that it's not possible to have come from a natural mushroom, because his father would never make that mistake. But he didn't understand how this could be. And then one day, he's at a party, and he overhears a couple of chemists talking. And they happen to be talking about stereochemistry, the molecules in 3 dimensions. And his ears perk up when he hears the word muscarine, which is the substance that is found in the mushroom. He goes over and tries to join the conversation and says, well, what exactly are you talking about, muscarine? And he says, oh, no, you wouldn't really understand. We're just talking about stereoisomers. And says, no, explain it to me. So one of the guys says that, this molecule muscarine, which indeed is found in the mushroom, can actually occur in two mirror image forms, which are non-superposable. They're not identical. And so the guy says, well, what do you mean? I mean, you find both of these in the mushroom? He says, no, that's what's interesting. The naturally occurring muscarine in the mushroom is only one of these chemicals. So then he says, well, how do you know that the other one ain't going to exist? He says, well, because it's been made in the lab. When we make muscarine in the lab, the consequence of the synthetic procedure is that you get both of these enantiomers. Now, this, of course, rings true to him, because then he begins to wonder whether or not someone had poisoned his father by putting synthetic muscarine in there. So he asked this chemist, is there any way to tell the difference? He says, yes, you wouldn't understand. There's try me. So finally, they explained to him that there's an instrument called a polarimeter. And this is able to detect whether or not you have two mirror image isomers or only one by passing light through and see the direction that the light is rotated. So, of course, right away, he asks, is there any place where this test can be done? So it says we have one of these polarimeters in the lab. So it goes down to the police, who luckily have kept a sample of the stew that had killed his father. They put it into the polarimeter. Sure enough, it turns out that it contains both of those enantiomers, meaning that it was synthetic, that it did not come from a naturally occurring mushroom. And then, of course, the police get into it and they find the criminal. It was a matter of money, of course, the will and all this stuff. It's an interesting story. But it's the only time in history that a criminal was caught with a polarimeter. So stereochemistry is very important. And to just see how important it is, if you go to Utrecht, at the university, there's a huge mural of Van Hoff. And as you can see, stereochemistry is featured. So that's the chemistry prize, 1901, the first ever given. The first ever prize given in medicine and physiology went in 1901 to Emil von Behring, again, German. As I told you before, I mean, Germany was the focal place of science in those days. And this is also one of the things that makes the Holocaust so unbelievable. That this was not done by some primitive society in New Guinea. This was done by the most advanced culture at that time in the world. So that's makes it doubly frightening. Emil von Behring was German. He was a physician, and he worked together with Kitasato Shibasaburo, a Japanese microbiologist who had come to Germany from Japan. And that was a very rare thing in those days. There was not much contact between Europe and Japan. But both of them trained under Robert Koch. Koch was one of the best known bacteriologists at that time. I mean, bacteriology was a very novel field, was started by Louis Pasteur. But Koch became a top-notch bacteriologist, and he discovered a bacteria that causes tuberculosis. That was a very big deal in those days. Tuberculosis was a terrible disease. And later on for this, in 1905, Koch would receive the Nobel Prize. But Behring, who had trained under Koch and knew a lot about bacteria, became interested in diphtheria. Diphtheria, again, is a terrible bacterial disease. It goes hand in hand with unsanitary conditions. In those days, there were a lot of unsanitary conditions. Diphtheria was a very, very serious infection. And very often it caused death. So this is what Bering was interested in. And he found a way to actually cure the disease. What he did was to inject some of the bacteria into a horse. And then, after a certain period of time, took out the blood of the horse, and from it isolated, which he at that time called an antitoxin. And today, of course, we would call that an antibody. What happened was that the horse, in response to the bacterium, to try to protect itself, generated antibodies, and those antibodies then can destroy the bacteria. This basically is the process of vaccination. So they would be able to isolate the antitoxin, as he called it, from the blood of the horses. And as you can imagine, this gave rise to some cartoons, because it's, you know, with many discoveries, at first people are suspicious, you know, they don't want to be injected with something that came from the blood of a horse, and see what, you know, he's draining the horse there, and people just waiting in line. But the fact is that they did work out the technology to separate the antitoxin from the horse, and that really the actual separation, the purification of this was masterminded by Paul Ehrlich, who also in 1908 went on to win the Nobel Prize for the first ever antibiotic that was introduced. That was salvarsan. Salvarsan, the name comes from safe arsenic, because what he managed to do was to incorporate arsenic into a molecule that would be absorbed by bacterial cells and kill them. So Koch went on to win the Nobel Prize. Ehrlich went on to Nobel Prize. The poor Japanese guy didn't, but he does have 1,000 yen note named after him in Japan. So Bering's discovery was huge, because children, particularly children at the time, were dying in droves of diphtheria. Today, it's much more rare, because of course we now have a vaccine for diphtheria, right? Your kids have gotten the DPT vaccine, which is diphtheria, tetanus, tuberculosis, right? So 1901, the first time that anyone was able to treat a bacterial disease in this efficient fashion. So of course he did deserve the Nobel Prize. So those are the Nobel Prizes given out the first year. But I want to tell you one more story of a Nobel Prize. I mean, of course, there are many, many stories to be told. And every Nobel Prize that has been awarded since 1901 has a story behind it. And we could give not one, but several courses on all of the Nobel Prizes. But there is one person who was unique, the only person to win 2 Nobel Prizes in 2 different disciplines, one of which was in physics and the other one was in chemistry. Who was that? Oh, yes, of course, Marie Curie. The only woman to ever win 2 Nobel Prizes as well. But 2 different disciplines. This is really quite something. The first Nobel Prize was in 1903 in physics. And that was together with her husband, Pierre, and also with Henri Becquerel, discoverer really of radioactivity, although the term radioactivity was coined by Marie Curie. Something else I should point out in this context here, the Nobel Prize can be divided maximum among 3 people. These days, that tends to be the case because there's so many candidates that almost all the science Nobel Prizes today are awarded to 3 people. But not necessarily. There have been individual ones. There's only one person in history who has won 2 individual Nobel Prizes, not shared. That's Linus Pauling. He won for chemistry, and he won for peace. He's the only one. So in 1903, Marie Curie, Pierre Curie, and Henri Becquerel shared the Nobel Prize for Physics. And then in 1911, Marie Curie won a 2nd Nobel Prize in chemistry, and this one was not shared. She won this alone. So let me tell you the story of Marie Curie, because it is indeed very interesting. And we'll start later in her career in 1921, when she came to the United States and was welcomed by President Harding in the White House at a huge reception, because by this time she was the most famous woman in the world. She was more famous than Kardashian today. And President Harding gave a speech welcoming her and gave her a gift from the United States, a very expensive gift. The gift was worth $100,000, which today would be $1.5 million, something like that. What was the gift? A small vial of radium. Now, this was the substance that she had become famous for. This was the substance that, along with her husband Pierre, she had extracted from pitchblende, a type of ore. Tremendous labor. They actually used tons of ore to finally extract a smidgen of radium. But radium was much sought after in research then, possibly for treatment of disease. And there just wasn't enough of it. But the United States, of course, which was already pretty advanced scientific country at that time, did have some. And Harding gave Marie Curie a box with supposedly the $100,000 vial of radium in it. There he is with the box, except that the box was empty. Why? Because radium is radioactive, and they didn't want to take a chance of the president being exposed to any radioactive material. So the box was just symbolic, it was empty. But they did, after, put a lead casing in it with the radium that she took back to France. And she did further research with it. But again, there's a background to this story. Because, as I said, science always builds on what happened before. And this was very well said by Isaac Newton when he was asked how he came up with so many good ideas. And he said, because I stood on the shoulders of giants. Well, the giant in this case was Henri Becquerel. And it was somewhat of an accidental discovery. He had been intrigued by X-rays, like, many scientists at that time were. But he had been studying a phenomenon known as phosphorescence, when substances glow, especially after being exposed to light. And one of these substances was an ore of uranium. Now, they didn't know very much about this at that time. It was just interesting that this rock, after being exposed to light, would glow. He was working with this. And one day he just put it aside on a bench. But it was a bench which had a drawer in it. It was a drawer where he kept photographic paper because he would take pictures of his experiments. He opened that drawer one day and he took out a photographic, what should have been a blank photographic sheet, and he saw a smudge on it, exactly where this uranium ore had been sitting on top, insulated by wood from the drawer. Something went through the wood. He didn't know what it was. It wasn't X-rays. I mean, he knew that rocks don't produce X-rays. So he started to study it. But he didn't publish much about it. He recorded it. And luckily, this came into the hands of Marie Curie, who was looking for an interesting project for her doctoral thesis. And she started to study this phenomenon. And she gave it the name radioactivity. She had married another scientist, Pierre Curie. And Pierre, who unfortunately had a tragic accident. Pierre was killed, run over by a carriage in a street in Paris. And she was, of course, devastated by that. But the early work was done together with Pierre. And Pierre had invented a device that could measure this novel kind of radiation. It wasn't a cathode ray, it wasn't an X-ray, something different. And he had invented a device called the electroscope that could measure this. So Marie became very interested in the kind of materials that would produce this sort of radiation. And of course, there was uranium, which is what Becquerel had found. But she wondered whether or not there were other such minerals. So she began to experiment with Pierre's new device and found that there was an ore called pitchblende. And this also gave off these mysterious rays. It also was radioactive. So she decided that she was going to find out what in there was producing this. So they started to basically break down this ore chemically, took different fractions of it, tested them with Pierre's device for radioactivity, and eventually found a very, very small amount of a substance that was responsible for emanating these mysterious rays. She's named this new substance polonium, after Poland, which was her native country. But even after they extracted all of the polonium from the pitchblende, some radioactivity still remained. So there had to be some other substance in there that was producing these rays. And she finally isolated a second substance, and that was radium. And she named it radium because it was like a ray, gave out rays. So that was radium. This, of course, is what made her famous, the discovery of radium. First of all, radium looked unique. It glowed. And she would always carry a small vial of radium with her and amaze people by its glow. This was not a good thing to do, as it turned out. But radium's glow was capitalized on by manufacturers who started to produce all kinds of glowing objects with radium. The paint made of radium would be applied to whatever you wanted to glow in the dark. Watches, of course, were ideal, because before this, it was very difficult to see a watch in the darkness. This made all the difference. It became a huge industry. Now, the watch dials were actually painted by hand by the radium girls, as they came to be called. It was not a good occupation. They would use very tiny brushes, obviously, to paint the dials. And to get a good tip on the brush, they would lick the brush and then dip it into the paint. And many of these girls developed cancer of the mouth. In fact, to such an extent that when they were buried, they had to be buried in a lead coffin because their body was radioactive. A movie was made about this, and it's called The Radium Girls. It's a very, very good movie. It is historically very accurate, and it tells the story of the Radium Girls. Now, of course, in retrospect, we always have 20/20 vision. But when all of this started, they didn't know about the dangers of radium. And then again, the quacks got into it because there was so much news about radium and its wonderful properties that they started to sell medications with radium. Radiator was one radioactive water, and it was supposed to be a cure-all. It wasn't. It would destroy your bones, as is evidenced by this guy. And unfortunately, Marie Curie eventually developed aplastic anemia from carrying around the radium and working with radium all the time. She, along with Pierre, are buried in Paris in the Pantheon. That was not the original place where they were buried. They were moved there from the cemetery. Marie originally had been buried in a lead coffin. But when they moved, by that time, of course, they had radiation detector equipment, and it turned out that she wasn't very radioactive anymore. So she's buried in here in just an ordinary coffin. The box that President Harding gave her is now located in the Curie Museum in Paris. And if you're ever there, you can go and look at it. There it is. No longer has the vial of radium in it. But that's how she got all that publicity in the US. But her discovery, the discovery of radioactivity, obviously had all sorts of spin-offs. Radiation treatment for cancer today is all based on that technology. And Marie Curie's contributions, of course, were immense. There's a very, very good movie about the life of Marie Curie. It's called Radioactive. I think I think it's on Amazon Prime. It's really worth seeing. It is very well done, and it's historically very accurate. So that is the story of the original Nobel Prizes and the first year that they were given, plus a little bonus about the only winner who ever won in 2 different disciplines, which was Marie Curie. There are all kinds of other stories about Nobel Prizes, and I have some of them on our website. You can always go there. And of course, you can go there to sign up for a free weekly newsletter as well. So that's our Nobel Prize story for today.